Welcome aboard the plane train.
This trip is a little more freeform, so I didn't really know what to expect. I was told, you're going to go see a 10-meter telescope, and I was just like, yeah, let's do it. Let's go see a 10-meter telescope.
Africa! Free boarding only, Delta Flight 200, non-stop service to Johannesburg, South Africa if you require.
I, hopped on a plane, and 15 hours later arrived in Johannesburg. Then took another plane, domestic flight in Africa, and then arrived in Cape Town.
And then you rent the car, and then you get the sense that the adventure is beginning. So you're going to drive out into the interior, 5-hour drive. And that takes you through some fairly barren ground.
It gets even more surreal when you look out your window, and on the wrong side of the road, there's also baboons just wandering down the highway. Like, definitely not something you see at home.
And then you get through the small town of Sutherland, a couple of blocks, and then about a 15-minute drive outside of Sutherland up to the top of the plateau where the observatory is.
Allowing students to get the experiences of observing using major facilities, but also it's just old-fashioned fun being actually at the observatory.
That fascination that you have as a child growing up looking at the stars, we just never grew out of it, and we now get to play with $1 million toys. It's super cool.
The Southern African Large Telescope, also known as SALT, an international endeavor.
That was the first really big investment in science in the new South Africa. They didn't just do that to build another sandbox for international astronomers to come and do their science. SALT has a much grander imperative, and that is to be a beacon for science and technology, not only in this country, but on the continent. SALT is the Southern African Large Telescope. It's not the South African Large Telescope. It's meant to speak to all of us.
That's great, yeah? That's wonderful. The Southern African Large Telescope is a good example, of how science can benefit, the general community and the nation, in terms of social and economic development.
When the new government came in after apartheid, South Africa invested very heavily in astronomy, and the idea was to try to get a lot of school kids to get excited about doing science, be it astronomy or be it something related. And to that end, SALT became very famous in South Africa. And so I think it's a great sign, and it's actually very rewarding to be part of that process and do a little bit of advancing science in a country like South Africa. So we're now just about approaching the gate.
They're phenomenal machines. They're so precision made and incredible. It's a little distracting to see it out the window right there. But it's kind of like appreciating where your food comes from. You need to see it. It's like I had an instrumentation class, and we studied this one pretty extensively because, we have a big partnership with it. But it's a whole other animal to see it in person.
Welcome to SALT. We'll do the unofficial tour. Let's see where the magic happens. Where all your data comes from. Hey, how are you? Good. Eric Wilcots.
Hey, welcome back.
How are you? Good to see you. And here we are.
Oh my God.
It's big.
Yeah, it is really, really big.
You've seen the pictures, but it just doesn't.
No, the pictures do not do it justice.
You get down on the knees and just be like, oh my God. So excited, I'm shaking a little bit, it's fine.
Badger sign there. This is a really big telescope. It's the largest one in the Southern Hemisphere. And the larger your telescope, the more light you can collect. And why is that important? Because the most distant objects in the universe are also the faintest objects in the universe from our perspective. The farther away an object is, we're seeing that object, that light that is reaching us now, is not what that object looks like now. It's what that object looked like a very long time ago. Farther out we can go, the farther back in time we can see. So really tracing back the origins of a galaxy like our own Milky Way.
I decided to go into astronomy at age 14, and lo and behold, this is a career field you can go into. Halfway through my PhD now. Got a little more time to go, but I get to play with stuff like this. I've used the Hubble telescope. Like, I've been one of the lucky people who kind of got my dream. Like, it's a dream come true, really.
Inside the payload is the main instrument for the telescope, and something we call the Robert Stobie spectrograph. It was designed and built at Wisconsin, but that instrument there is Wisconsin's main contribution to the initial construction of the telescopes.
The spectrograph is to astronomers as a scalpel is to a surgeon. The key thing we want to do is develop our instrumentation capabilities, and given their expertise and their long history in that, it's hugely valuable to us to have that in the family, and working with Wisconsin on that is a no-brainer.
Wisconsin has contributed so much. The science, developing the instruments, the human capacity, like professional development of our scientists and our students, PhD students, and also in terms of social programs like education, empowerment of our teachers, exposure of our learners, and I would love that to continue.
You can see the curvature of the reflection of the structure in there. The instrument, the telescope, is initially driven by a desire to do great science. Right? There's some, you want to be able to answer some important scientific questions. So as the sky gets darker, the first stars will come out. The telescope will acquire one of those stars to do some initial calibrations, and then we'll embark on the night's journey of going through 6, 7, maybe 8 different scientific projects that will be done tonight with this telescope. And it'll be done by our collaborators in the partnership from around the world. For humans, ever since the very beginning of humankind, we have been fascinated by the sky. And I think you hear that in the stories that we've heard around here, the one of the indigenous people who looked up in the sky as someone taking a fire and throwing the ashes up into the sky, and that gives us the embers are now the bright parts and the ashes are now the dark parts of the Milky Way. And modern astronomy is just the extension of that. And it's great to be continuing that long search of humanity to realize our place in the universe.
I spend a lot of time in my research looking at things that a lot of people would say, well, why do we care about this? Why do we care about this cloud of gas and dust floating out in the Milky Way? And the important thing is that's where we came from. So all of those interesting molecules that were floating in that cloud, things like ammonia and benzene and silicates, the rocks you can find on the ground, those are just large conglomerations of silicates. And by studying these things at the largest scale, we can understand where we came from. So we're seeing the Earth's, maybe not baby pictures, but the ultrasound of the Earth before it was born, so to speak, when we study these other stars and other molecular clouds.
Let's go into the control room, and this is where all of the action takes place during the night. Telescope's up top, and here are our telescope operators, Tia and Raz. This is the control room. And right now we're observing a project led by some of our collaborators from the United Kingdom, and the idea here is to get a spectrum of a star called WASP 40. Do we know what constellation that's in? No. Okay. So why would anybody want to look at a star called WASP 40? Well, you have an image of the star, which you can see on this screen right there, and the red line shows us where the slit of the spectrograph should be positioned in order to get a good spectrum of it. So this particular star is being looked at for something called chromospheric activity, and that is the type of magnetic activity that we are kind of used to thinking about on our own sun in terms of solar flares and sunspots and prominences. Looking at something that's very chromospherically active like WASP 40, we want to see how active is that thing, and then what does that imply about the conditions that might exist or a planet orbiting that star might be subjected to over the course of its orbit. And that feeds into this thinking about how habitable a potential planet might be. So we're collecting the data from it. How long are we going to be looking at this?
10 minutes.
10 minutes, relatively short exposure, but that's when you have a 10-meter telescope, you can have short exposures. Right.
If it weren't for this formation process of the galaxy, we wouldn't be here today. we wouldn't have the materials that formed in stellar crucibles that then were ejected back into the Milky Way, then eventually coalesced into stars and formed planets and got us to the Earth we have. So there's this kind of intimate link between the largest scales of the universe and the smallest.
You're not going down to about 37.
It always feels a little bit like a kid in a toy store when you sit in the control room of a telescope, especially one as massive as SALT.
So that's the supernova.
Wow. Really?
Yeah, yeah.
We saw this supernova that went off relatively recently, and it's pretty rare to see that, and yet we were here for that moment, and it came right off the telescope.
This is a star that's exploded. It's actually a binary star, mass transfer, and we get this explosion. Inside that eruption, as part of that process, that star was able to form key elements, gold, uranium, things like that, those heavy elements. All of that material was formed in a star. And if we think about one of the things that we see in South Africa, well known for its gold mines, where did that gold come from? That gold came from a supernova. Sometime before the formation of our own solar system, somewhere in the galaxy, a supernova erupted, spilling out those heavy elements that somehow, through a process that we're just now beginning to understand of planet formation, got incorporated into the Earth, incorporated into the continent that we're standing on. Right? And so the organic material that gave rise to life on Earth, that is organic material that we see in space. And so we are tracing really the basic origins of our planet, the origins of life, by looking out into the universe.